Welcome! The object of today's class is plate tectonics, a powerful theory which allows us to explain and predict a large number of phenomena taking place in the Earth. The similarity of the shapes of South America and Africa across the Atlantic has struck the imagination of scientists since centuries, and is a clear demonstration that parts of the Earth thousands of kilometers across can easily move around the Earth. You're all familiar with the GPS, the Global Positioning System. Communicating with a network of stationary satellites, the GPS allows you to know where you are and to measure distances between points. Since the moment it started being used at a massive scale, we have now GPS stations spread all over the world, providing a huge amount of data, constraining with an error bar of less than a few centimeters the horizontal and vertical position of points across the Earth. This map shows you the displacement per year experienced by specific points with respect to an absolute system of reference. On the map, you can find domains where displacement vectors have similar orientation and magnitude, suggesting that these points lie on a rigid plate. This is the case, for instance, of the Pacific domain. If you move towards the west into the Australia region, you see that displacement vectors are very different. The Earth is then subdivided in rigid regions with little movement between one point and the other, separated by narrow domains across which vectors are very different. On the base of GPS movements, we can subdivide the surface of the Earth in roughly 12 major domains with little relative movements, called tectonic plates. These are separated by narrow zones of strong relative movements which act as boundaries between the plates. As we will see, the margins accommodate different types of movements. GPS describe very accurate movements at the Earth's surface during the last decades at most. But when did these movements start? Have these movements always been going on? And since when? Studying, among others, rocks and fossils, geologists provide an answer. Geologists have discovered, for instance, that very similar fossils can be found in South America and Africa. This is obviously incompatible with the presence of a large ocean between the two continents. Very provocative ideas have been proposed, such as that of 1,000 kilometers long bridges connecting the two continents. These fossils are 300 million years old and show that at that time the continents must have been together. Once scientists learned how to bring the continents back to their original position, a lot of more peculiar phenomena started making sense. Rock bodies with strong similarities presently outcropping on the two sides of the ocean turned out to belong to the same zone. Towards the beginning of the 20th century, it became accepted that continents had moved, and in the 60s, the theory of plate tectonics was formalized. Scientists presently agree that the outer part of the Earth is fragmented in a limited number of wandering major plates, and that similar processes have been going on during the last 600 million years. 300 million years ago, for instance, the plates were all together, forming the megacontinent Pangaea. Note that plate movements have changed during all this time. As a consequence, the number of plates has changed through time, and the nature of margins has also changed through time. What are these plates? To provide an answer to this question, we go back to what we've learned on the structure of the outer part of the Earth. Which one is the rigid part? And which are the layers and rocks on which the rigid part move? Let us start from the surface and we move downward. The crust on which GPS measurements are taken is underlain by mantle rocks, separated by the moho discontinuity. Rocks above and below the moho are solid and are well coupled to each other, thereby ruling out the possibility of relative movements between each other. We need to go deeper. At higher depths, the rigid and strong rock of the lithospheric mantle pass downward to the low velocity zone, where rocks have a small percentage of melt. These rocks are softer than the surrounding and form the soft substratum on which lithospheric plates move. The plates of plate tectonic theory are therefore lithospheric plates. Welcome. On the map, you see the main tectonic plates forming the outer part of the Earth and the narrow intervening zones characterized by strong deformation. Today, we will focus on divergent margins. Divergent margins are zones where the two lithospheric plates move away from each other. Typical divergent margins are in the South Atlantic, separating the South American plate from the African plate, and in the East Pacific, where the Pacific and Naxa plates move away from each other. The East African Rift is a zone of extension which, given sufficient time, will develop in a divergent margin. Divergent margins are zones where the two plates move away from each other and form a belt of submarine ridges thousands of kilometers long across the entire Earth. The space created by the movements of the two plates away from each other is filled with new magma from the asthenosphere. Volcanism is indeed one of the characteristics of oceanic ridges. Divergence and rise of magma are associated also with widespread earthquake activity along the plate margins. Earthquakes are generally not very large and generate at depth shallower than 5 to 10 kilometers. Divergence margins begin with the onset of extensional faults breaking a continental plate. The structures formed are called continental rifts. The East African Rift, which runs for thousands of kilometers from the Red Sea to Southern Africa, is one of the best known examples. Ethiopia, Kenya, and Tanzania are moving to the east with respect to the main body of Africa, forming a zone of extension flanked by normal faults. A rift is a sinking zone flanked by normal faults. The domain moving downward is called the graben. It is an area of increased accommodation space where sediments can be deposited. These sediments are called syn rift deposits. The region flanking the graben are called horsts. It seems that the first human beings highly appreciated the East African Rift. Lucy, considered to be the mother of all human beings, was born and she lived here. Rifting begins with the activation of normal faults associated with crustal thinning and the consequent subsidence of the central graben. With persisting extension, displacement along faults increases, more subsidence occurs in the central domain, and a thick package of syn rift sediments is deposited. In some cases, extension ends and the continental rift becomes extinct. If subsidence continues, new accommodation space is created, in which sediments are deposited, which are not cut by normal faults. These are called post-rift sediments. This is the case, among others, of the Viking Graben between Norway and the United Kingdom. In other regions where divergence does not stop, the crust and the lithosphere become increasingly thinner. When lithospheric thicknesses of 20 to 30 kilometers are reached, the lithospheric plate breaks, and the initial continental plate is now split in two plates. A divergent plate margin is created. Driven by decompression melting, large quantities of magma are formed, which fill the space being progressively created between the two plates. From this moment onward, the divergent movement between the continental masses will be taken over by the divergent margin. Faults in the continental domains will not be active anymore, and the margin has become passive. As the two plates keep moving away from each other, the new oceanic crust will also move away from the mid-oceanic ridge and will cool down. With cooling, it will become denser and gradually sink and increase in the depth of the ocean floor. Because oceanic crust is generated only at the plate margin, the age of the crust will increase moving away from the ridge. The older the oceanic crust, the heavier it is, and deeper is the seafloor at that locality. The map in the picture shows with different shades of blue the depth of the ocean floor. If you take the oceanic ridge running along the Atlantic, you see how depths increase away from the ridge itself, in accordance with the principle mentioned in the previous slide. If you would then compare this map with maps indicating the age of the oceanic rocks, you would see how regions with deep seas are floored by old segments of oceanic crust. Away from the oceanic ridge, the oceanic crust passes to continental crust, which has been stretched during extension, which preceded lithospheric breakup. These are passive continental margins. Here are the most important features for you to remember: normal faults, syn-rift sediments, and post-rift sediments. Let us now make a summary of the evolution of divergent margins. Before rifting starts, the crust has a constant thickness, and the Earth's surface is typically close to sea level. With the onset of rifting, normal faults are created, which cause crustal extension and subsidence in the central domains. This is the syn-rift stage, and associated with thinning of the crust and of the lithosphere. If extension ends at this stage, a continental rift is created. The North Sea is a famous example of a fossil continental rift. If extension continues, the lithosphere becomes so thin that it can break, leading to a formation of a passive continental margin. Between the two fragments of continental crust, progressively younger oceanic crust is formed. Welcome. We'll focus today on regions where two adjacent tectonic plates move towards each other. These are convergent or active margins. A well-known example is between the South American and the Nazca plates. The first is continental and therefore light. The second is oceanic and thus heavy. In these cases, the oceanic plate descends underneath the continental plate. These are subduction zones. Convergence can take place at rates larger than 10 centimeters per year and has been going on for millions of years. You can imagine that a lot of interaction must have taken place between these plates. It is not a surprise that convergence zones are also called active continental margins. There are three major types of phenomena taking place at active continental margins: volcanism, earthquakes, and crustal accretion. Volcanism is one of the most apparent features of subduction zones. Volcanoes are found all along active continental margins and are always located on the upper plate of the subduction zone, tens of kilometers away from the convergence zones. What are the processes linking volcanism to active margin? This has to do with the relations between melting point and magmatism we have discussed in a previous clip. During its downward movement, the subducting plate brings fluids contained in sedimentary rocks down to large depths. With increasing load of the overlying rocks, the fluids will be squeezed out of the rock, will migrate upward, and will lower the melting point of the overlying upper plate rocks. These will then melt and generate magmas, which will rise and form intrusive and extrusive rocks. Earthquakes are a constant feature of subduction zones. They are mainly caused by the friction between the subducting and the overlying plate. In an initial stage, called the loading stage, static friction prevents slip between the two plates. The continuing convergence between the plates causes vertical movements in the upper plate and increased stress levels at the interface between the plates. Once the accumulated stresses overcome friction, slip will occur at the interface between the plates, generating large earthquakes. Large portions of the contact between the two plates will fail, releasing the huge amount of energy associated with earthquakes in subduction zone. As a result of slip, the upper plate will rebound, moving upward at rates of meters per second. One of the most destructive consequences of earthquakes are tsunamis, which are generated by the sudden upward movement of fault blocks. Huge water masses are suddenly displaced, generating waves which travel at velocities of hundreds of kilometers per hour over huge distances. In the case of a major earthquake in Alaska, the tsunami waves reached the coast of Australia 15 hours after the event. The third major feature associated with subduction zones are accretionary wedges. Because of the friction between the subducting and the upper plate, sediments and other rocks of the lower plate are scraped off and accreted to the upper plate. Not surprisingly, rocks in the accretion wedges are highly deformed, and they form the initial stages of mountain building. Subduction zones in the world all share the three features mentioned above. Some other features are, however, different and have led to the definition of two end-member, Andean type and Pacific type subduction zones. The main difference between the two is the position of the subducting plate, which is gently dipping in Andean type subductions and steep in Pacific type. A second difference between the two types of subduction zone is observed in the upper plate. The upper plate in Andean type is continuous and above sea level. Upper plate of Pacific type subduction, on the contrary, typically displays a marine basin. This basin is associated with extensional faults. The last issue I want to mention is that of the evolution through time of subduction zones. Some subduction zones continue for a long time without major changes. This is the case of Japan, where the Pacific Oceanic plate has been subducting underneath Eastern Asia during the last 200 million of years. In other cases, when the oceanic crust laterally passes to continental crust, the two continents approach each other. When the continental crust arrives into the subduction zone, the lower and the upper plates have similar densities, and smooth subduction becomes difficult. Continental collision occurs, leading to the formation of the large mountain belts of the world.